Okay, so now we're recording. So let's apply energy ideas to a situational block that was released from rest at top of an incline. To start with, we'll assume that the block slides down the ramp without friction to make things easy. So we're simplifying the situation here. Just to simplify things. Our goal will be to graph energy as a function of distance traveled and as a function of time. Okay? If we're doing that, let's think about what we can learn from equations we already know. So remember, constant acceleration, and in the special case of initial velocity is 0. So remember, this came from this. But remember, we assume.
So, Mashne?
Yeah, go ahead.
I only have one lab. I don't have that one.
You don't have this energy conservation one?
No, I have collision simulation.
You have to flip through the week 3. It's near the end of it.
Yeah, near the end, actually, yeah. Sorry.
Okay, thank you.
Yeah, I may put it as all as one. Yeah, now I remember. It was very ambitious that I want to do momentum this week because there's actually a virtual lab with it. I want to save it for next week. So my bad. I should have actually realized I saved it all. So you guys can see it now. Cool. Yeah, but I don't remember how I photocopied it. So you remember, we assume V0 equals 0. And D is the same thing as x minus x0. Same thing. So that's what's happening in that equation. And of course, this one comes from this. And if you move x and x0 to the other side, remember V0 is 0. And that's just D. So, and of course, velocity equals acceleration times time because that came from that, and that just goes away. Then V equals AT. So those equations we already should know. That's from week 1. The new ones, kinetic energy and potential energy. Some people use the letter U. I'm not sure where that comes from. Some people use that. You can call it PE. I don't really care. You call it kinetic energy KE. And this right here is another form we can use. We call it work kinetic energy. So this is basically when work equals kinetic energy. That's another form we can use as well. We keep moving. So now you're told make use of these equations to sketch graphs of energy versus distance traveled and energy versus time for a block sliding from rest down a frictionless plane. Define the 0 for gravitational potential energy to be the bottom of the ramp. And plot potential energy connected to total mechanical energy. Okay, so we're actually going to do 3 different graphs here. Our potential energy is going to be in red. Our kinetic energy is going to be in blue. And total mechanical energy will do in green. Okay. So let's first focus on potential energy. We'll do this in red. So, so the energy as a function of distance. Okay. So in this case, if we focus on potential energy, so we'll do red for that. So PE. And we can think of our H like distance. Because that's actually the distance we're going to travel. And you're on a ramp. So let's draw a picture of our situation here. and you have an object, and it's rolling down. So before it rolls, we can assume, so does that rest, right? And this should at rest. So what percent of our energy would be kinetic, and what percent would be potential at the start? So I'll just call on whoever I see on my screen here. So Steve, I see you. So at the top of the ramp, it's not moving, so there's no motion. What percent of our energy is potential, and what percent is kinetic?
If it's not moving, then shouldn't it all be potential energy?
You're 100% correct. Yep, no pun intended. You're 100% correct. Yes. So it's 100% potential energy at this point. 100% PE. So going back to red here, I'll kind of assume it's like that. And remember, this is our distance, right? So right now, our actually, hold on a sec here. It's actually going to be up here. So that's our height. And of course, when it gets down to the bottom of the ramp, so the one I see next, we're at the bottom of the ramp. What percent is going to be potential? So now we're on the ground. What percent is potential? What percent is kinetic?
There'd be no potential energy and all kinetic.
Yep, 100% correct. Again, no pun intended. So, yep, because now it's just full steam ahead by the time it hits bottom of the ramp. So, so we expect when the distance is 0, we expect to have 0 potential energy. And how you actually draw it, I mean, if you think about it, it's kind of a linear relationship, right? Or constant times distance. Because M and G don't change. Your acceleration or acceleration to gravity is a constant. And it's not like the mass is being added on. It's not like you're adding mass, so it's going down. So yeah, so you could draw a straight line actually. Now for the kinetic energy, that's going to be a little bit funky here. Remember what we have for v squared. So let's actually use blue now for that one. Remember what v squared equaled? It was going to be 2AD. Go ahead.
Shouldn't potential energy be the other way, where like it starts off really high?
That's with time.
Energy is being used.
That's going to be this one.
Down.
That's going to be this one here for time. We're looking at distance right now.
Oh.
Actually, you know what? Let's do it simultaneously. That's a good call. You're talking about on the right side. Yes, initially it's all potential. By the time this is going to be the time it takes to reach the bottom of the ramp. But the other one, because when you're distance off the ground, so this distance, vertical distance, mind you, from the ground. That's what the graph on the left is going to represent. Now let's go back to blue. So V squared equals 2AD. So your kinetic energy, if you do a kind of a substitution here, will be 1/2 times your mass times 2AD. The 2's cancel. And your acceleration really is just going to be gravity, if you think about it. That's the acceleration we're dealing with here. So your kinetic energy is still going to be mgd, so it's still really the same thing, right? But because it's 0, initially we have 0 kinetic energy. But by the time you get to the bottom, it's going to be 100% kinetic energy. It's going to look just like that. Whereas when my distance is 0, when I'm at the bottom, it's obviously all kinetic energy. So it's essentially it's a trade-off. That's what we're noticing here. So now the question is, what do you guys think about the total mechanical energy? How would I draw that? Which is the green line.
It'd just be like just a straight line.
Horizontal line, yes, 100%. Yep, because remember that's conserved. Yep. So that's what we expect for our energy versus distance or energy versus time graphs. Of course, the reverse for kinetic potential, because the way we're looking at distance, d equals 0 means right at the bottom of so this is the bottom of the ramp. That's the top of the ramp. At t equals 0, obviously that's the top of the ramp, and that's the bottom of the ramp right there. So now if we look a bit further, if the block slid for twice the distance and Frick's ramp of the same angle, the kinetic energy would, compared to the original, be increased by a factor of, well, if you're doubling the distance, right, you're doubling the height, because you're keeping the same angle. So you're doubling the potential energy, so you're really just doubling the kinetic energy as well. So really what's happening is that when you twice the distance, that's twice the height. So P times 2, so KE times 2. Remember, you just have to conserve it. So that should just be double that one. And here, if instead the block slid for twice the time down the frictionless ramp at the same angle, so let's look at, I'm going to clear all this right now. Actually, you know, I made a mistake with time, the time graph. I just realized this right now. So this is correct, just so you know. I did this correctly. I made a slight error with the time graph. Can anyone tell me what error I made? I should not have done straight lines, by the way. What should I have done? Well, let's think about it. Your distance equals 1/2 AT squared. So my potential energy, m times g times my distance, we'll call it AG. So you have these constants. You have 1/2 times 1/2 times g squared times t squared. All that is a constant. So how are time and potential energy related now? Should it be a straight line or something else? So Liz, we'll call on you. How should I connect those two red dots? Given that P equals a constant times T squared. So I'm squaring the time. So what kind of shape do you think I'll get for the graph between the two red dots? Think about this right here. You have y equals x squared. What kind of shape is that? So you remember y equals x squared, right?
Mm-hmm.
What kind of shape does that have?
Parabola?
Good, exactly. It's the same thing here. Because isn't your potential energy on the y-axis?
Oh, yeah.
Your time. So it's the same exact thing. So it really should look like that. So I kind of goofed a little bit. I should have been more careful. Yeah, I kind of just assumed it's going to follow the same thing. So please make a correction to the graph on the right. That's my fault. So Kinect's going to really follow the same thing, but it's going to be going in the opposite direction. Because then you don't have any kinetic energy and hits a peak. And of course, the total energy is conserved. So that's really what we should be seeing as you go down the ramp. So again, that was my fault. I should have been more careful about that. So now to answer the question, if it took twice, so that for twice the time, so it actually is going to increase fourfold. Because remember, your energy equals a constant. So you're producing more energy as a result. Because it's working for a longer period of time, but it's going to be increasing fourfold.
Wait, so if the time was doubled, but it went the same distance, the kinetic energy would be quadrupled?
Exactly. Yes, that's 100% correct. Because it's spending more time doing work. That's why. Yes, it will. Yeah, I mean it's moving slower, but still it's. Yeah, and I think we assume everything else stays the same, right? Yeah. So, and then, oh, actually, we look like we do have a demonstration with you here. Okay. So actually, we could go through this. So let's see, we have a ramp. Why is this not working? Right, there we go. Okay. So they actually reversed it compared to the way I had it, which I thought was interesting because I'm assuming, the potential, right? If you have, okay, so they did the bottom of the ramp right here, and that's the top. No. Okay, so they just flipped it compared to the way I had it, because the way I was interpreting it, that is interesting. Yeah, because I had the the bottom of the ramp on the right and the top of the ramp. Yeah, so I guess they were interpreting a little different, but it's still the same trends as you see. So I think that's really what matters. But that is interesting how they did it that way, because I was assuming, yeah, so if you have x equals 0, yeah, hold on.
Mr. E,
That would be the bottom. Yeah, go ahead.
is it maybe because the way they did it is that like X or like 0 centimeters is like the top of the incline?
Yeah, they probably define it as that, as my guess, because I'm thinking of change of position. Yeah, yes, that's probably, yeah, but that just seems weird to me, because usually we don't measure position that way. So, but you see a trade-off. I think that's the most important thing. So, but we do see the more curved nature, of course, because given the relationship between time and energy. So let's come back here. So I guess we could say, our graphs had the same shapes, but different directions. The simulation assumed top of ramp at as the bottom of the ramp. So, yeah, I think we'll do a lunch break right around now. Yeah, this is perfect, because we'll do part 2 when we get back from, and I'll probably have you guys do that in groups. Yeah, part 2 would be great to do. And I think, is there a simulation? Yeah, I'll kind of walk you through that one. So yeah, let's come back right around noon. We'll say sometime between 12 and 12:05, we'll start up again. And then we'll do the second half of this, and then we'll look at 3.3 as well. Okay, I think we'll take a break right now.